Thanks, Hubert. I appreciate it. It's a pleasure to be here and kick off a fun set of speakers with Albar, Rob, and Paul. When I was in the airport the other week, I picked up a book by one of Michael Lewis's books, and it was on behavioral psychology and Daniel Kahneman and so forth. And I've found in reading it, it's like you get the most insights when you sit and learn stuff you have no idea about. And so maybe that'll be a little bit of what happens in here, because we've got all these dispersed talks across all these different fields. So I'll talk about today effects of stormwater capture and use on urban streamflows. I'll talk a little bit about why we care about stormwater capture and use, and it's sort of a topic of interest of late. And additionally, what we've been why this is important for Los Angeles and how it fits into the overall effort we've been doing. So I'm now at the Office of Water Programs at CSU Sacramento. It's a decades-old office. It's been around since it was started by one of the engineering professors there. It was started to do continuing education for wastewater treatment operations, and we do a lot of stormwater work now and a little bit of water resources work as well. And then I'm also a visiting researcher at UCLA, and previously I worked as a postdoc there as well as a research director. And so that's what I'll talk about a little bit today, some of the work that's coming out of this, and sort of an insert of urban systems modeling and urban hydrology modeling into the CWEMF agenda. So I'll make sure I'll recognize the big cast of characters that's been involved in this work. It's about a decade's worth of research that I had the opportunity to join 4 years ago that spans University of Utah, Colorado School of Mines, and UCLA, as well as a number of other collaborators. So Stephanie Pinsettle runs the California Center for Sustainable Communities at UCLA, where I worked. And then Mark Gold is the Associate Vice Chancellor for Sustainability and runs the Sustainable LA Challenge. They're both PIs on 2 of the projects we'll talk about here. And Katie Micah, who was a postdoc at UCLA, now at the mayor's office as the Water Sustainability Policy Officer there. And Madeline Glickfeld, who has been in California water for a long time, up here in Sacramento and down in LA, and she's the Water Resources Group Manager at UCLA. And then Diane Pataki and Lisa Litvak. Diane's a tenured faculty, Urban Ecology, so bringing in a little bit of the landscape picture. And Terry Hogue, you might know, a well-known hydrologist at the Colorado School of Mines, formerly at UCLA. And Kim Manigo, who's now a consultant back in California and lives in Bakersfield and works in California. So a big group of people we had involved in this, and that's the only way you kind of get these large integrative studies done these days. First thing we have to talk about, whenever you hear a study about Los Angeles, if there's one thing you remember from my talk, is when someone talks about Los Angeles, you have to say, which LA? And it's almost never delineated, okay? So we have LA County, a very stretched out LA County. It's probably a little more condensed. LA County, which is a whole shaded region right here, about 10 million people. The metro area is right here, so this is about 9 million people. So metropolitan Los Angeles encompasses about 88 different cities and unincorporated areas, about 100 large water supply districts, 200 or so when you include all the small ones. And then LA City, right here, is the one you most often hear discussed within research studies, especially on water. Why? Because it's a limited number of agencies, and getting them to work together, although maybe not any less challenging, at least you only have to talk to fewer people. So LA City is about 4 million people, and that's the LA Department of Water and Power, LA Bureau of Sanitation. But when you go out to the metro area or the county level, the analysis gets much more complex, and it lends itself much more to the types of modeling that we do for systems analysis of California at a broader scale. LA in itself, the complication of the governance system there, it's simply a macrocosm, essentially, of California across the state, right? So all of the challenges you see about integration and integrated water management and so forth get exemplified here. Stormwater capture in Los Angeles has been done for a long time. Going back even as far as the 30s, there have been concerted efforts for a managed aquifer recharge within LA County. And It's all built into the large-scale drainage network here, which is depicted in this representation. Each time you see one of these green boxes right here, that's a stormwater capture basin. There's about 25 or so of them throughout the county. They're capturing on average about 200,000 acre-feet a year. There's been some significant efforts, some really nice studies by LA County to figure out how to increase that further in future years and looking at climate change and so forth. But it's also subject to the geography and topology of the basin. So if we look generally here, there's a number of main watersheds. You have Bayona Creek here, runs out kind of towards Santa Monica is right here. You have the Dominguez Channel down here. It's kind of a little bit west of Long Beach. You have the LA River Basin right here coming through down, and so it encompasses Los Angeles City, and Los Angeles has a unique set of old rights to be able to get port access. So it has a little string of LA City that runs down along the river for right-of-way down here. And then Long Beach is over here. You have the San Gabriel River watershed flowing here. Okay, so those are the main watersheds in Los Angeles. Each one of these has some level of engineering infrastructure. Each one of them has some level of altered channels with it. But the stormwater capture basins kind of are located all throughout this area. So some of the main large ones here are at the intersection of the upper basins and the lower basins in LA. And this is the Whittier Narrows, several large facilities right there. Rio Hondo, that's often what you hear about or see pictures of. But in actuality, there's basins spread all through here. Some of them were originally flood control basins, and LA County is working on reoperating those to capture more stormwater. So water generally moves from here down through here. Now, in the historic, LA County has a number of adjudicated groundwater basins, one of the first areas to do that in the state. And in the historic development of these adjudications that divvied up the pumping rights, they tended to go upstream, right? So why? Because down here, these folks are at the end of the pipe. If you use more water up here, if you capture more water up here, then the folks down here who are pumping are going to be the ones who run out of water first. So there's an intimate relationship between capturing stormwater, trying to recharge groundwater that supplies critical water supply, and the integrated management across the basin. So we'll talk a little bit about that. We wanted to figure out a primary question which LA is grappling with right now. It's what's the potential for local water reliance, i.e. what's the potential to cut imported water? So we have lots of statewide discussions right now on Cal Water Fix and everything else, but the agencies within LA County, many of them, Santa Monica, Department of Water and Power, are looking at maximizing the use of local resources because they're looking out 20, 30 years and saying that water from the imported source is getting more expensive, it's getting potentially less reliable, we're not sure if it's going to be there, so we're going to look at even further maximizing our local sources. So that's what we wanted to kind of empirically investigate at a large scale. This work has been going on in the county for 5, 10 years. The university brings, and the academic perspective on this brings the opportunity to integrate across all these different jurisdictions in doing this. We created a number of studies, a number of different approaches, interviews, modeling, urban hydrology modeling, systems analysis modeling, and program evaluation of ongoing work. And we've put them all together in this big compilation of studies we're sort of rolling out right now. And this is one of the main tenets of it. It's called ARTIS. It's short for either one, artesian well, which is an original source of local water in Los Angeles, or art and science. Art is modeling is the mix of art and science a little bit. So a translation of that term. You've got pretty much the whole system compiled in here with the best representation that you could get. It's a monthly model, spans about 25 years of hydrologic records. Encompasses the stormwater, all the different water retailer agencies, encompasses wastewater operations, details the groundwater basins for the extent that we have an understanding of their function and operation. And we've used it in a lot of different ways. Now it's a model that runs on a laptop. It's not highly computationally intensive. It uses some of the latest software which benefits from that. So Gurobi, Python interfaces, NumPy interfaces to go back and forth, so it benefits. But ultimately, I did all the stuff on my laptop when I was running the model. And there was a reason for this in both developing the model for an integrated study and working with the people we worked with, is that the use of modeling isn't always accepted. That's the easiest way to put it. So I worked with folks who kind of wondered, what's really the usefulness of this? In order to do that, we had to simplify and limit the number of assumptions down to a very minimal few to be sure that we provided the greatest flexibility in understanding what were the possible actions that weren't necessarily a precondition of existing systems. Because that's the idea here. We're looking at a significant change, basically reoperating 100 years worth of infrastructure that's performed reasonably well in Los Angeles, right? So those inherent assumptions were important to try to question, and the way we could do that was to simplify assumptions, and it actually led to a fairly straightforward network modeling approach. So we built lots of different versions of this. We've got it that maximizes local supply, so it maximizes the flows from local sources, groundwater basins, stormwater capture, and so forth, to meet demands. We also built in hydroeconomics, so we put in all the annualized costs and ran it to minimize costs. We've simulated groundwater exchanges, groundwater pool exchanges. So we'd look at intersecting an undirected network within a broader directed network, meaning in directed networks flows just go one way, but you implement in the opportunity for market exchanges. And so we've got lots of different versions of this. It's all up on GitHub. All the data is there as well, and the website will be there, and I'll have the website at the end. So we use it for lots of different purposes. We wanted to look at the supply sources and what are the different supply source outcomes from running the model on these different goals. We want to look at the effects of conservation and also the feasibility of conservation. So in order to figure that one out, you had to understand what trees and plants use in terms of water over different conditions. And Diane and Lisa's work came in here. It was really important. They did multiple years of experimental field studies where they actually measured tree and turf water use. They have some really nice papers out that look at tree-specific water use in the LA and Orange County basins. And then you can create graphs looking at, this is graphing shortages across scenarios of supply and demand, and you can run this over these multiple models. And it fits into this idea of modeling for the Anthropocene, you might say, is you need multiple models to be able to try to evaluate what's really going on, and the smart strategies that we still luckily have the opportunities to make decisions upon. So given having a little bit of that background as to kind of the size and the scale of the modeling effort, one outcropping of this is I took and analyzed some of the results to figure out what are the effects of stormwater capture and use on urban stream flows. Now, for those who aren't aware, there's a huge statewide push on stormwater capture and use right now. The State Water Resources Control Board, the Storms Group, has a multi-year project looking at benefits of multi-sector benefits of stormwater capture and use, barriers to stormwater capture and use, and it fits into the other side of the regulatory hammer around what's developing called reasonable assurance analysis for new stormwater permits. And the Department of Water Resources as well has been looking into actually chronicling all the stormwater capture facilities, all the stormwater capture and use facilities that are currently in operation. So there's a number of different agencies that are working at this at the state level, and it's capitalizing on local agency efforts for this. So it's sort of a relevant topic, especially relevant in LA. And this gets the idea that there's trade-offs. Right? That local water reliance is certainly good, but you have to think about the system as a broader whole. So here's some results from two different formulations of the model. One that's maximizing the flows from local sources, and one that's minimizing the costs of supplying. So you're going to get more conservation here, because conservation is still a fairly effective way to mitigate costs from imported water cuts. Okay, and so you can see the details of the scenarios that these are being mapped. This is a scenario that has a 27% demand reduction from 2010 levels, so about equivalent to drought usage. And this one also has a 30% cut to imported water. So from those historic imported water levels, a 30% cut. And this one has a prescribed cut of 50% imported water. So there's not as much supply available, but the minimizing costs figured out where the conservation occurred with the stipulation of meeting health and safety demands. And you can see here how these two formulations, which do reflect alternative policy goals in the basin, may have some effects on stream flows. So we're comparing the simulated hydrology model from LA County, the results from that, which is based on calibration, with the optimized flows for local water reliance based on maximizing local supplies or minimizing costs. So what do we see here? When we're maximizing the flows, it's moving more water through the system, trying to figure out, probably a little bit unrealistically in some places, getting that water to the capture basins to get it in the groundwater. And you see up here in these upper basins, you actually have more water, because it's really trying to figure out how it gets any of that water in there. So building canals through the forests, whatever would be the actual implementation of this. Down below here, though, you see a lot less water in terms of, this is volumetric for acre feet. So 50,000 acre feet, this is somewhere between 50,000 and 10,000 acre feet less as the median change between the simulated historic and the optimized values. Now over here, it gets a little more drastic. Why? Because there's more conservation and you see more reductions up here. The only difference here is Sepulveda Basin, because we implemented a new piece of infrastructure that's being discussed for stormwater capture in Sepulveda Basin. So what is this telling us is that if you're looking to maximize local water reliance based on building lots of new infrastructure, you're going to see potentially, you have to figure out what to do up in the upper basins, but down here it's likely that you'll see a change in less stream flows. And this is actually completely the opposite of what was being discussed here for this very key channel, which is the LA River, where we want to figure out how to have perennial, like all-season flows for support recreation and economic development and so forth, right? So this is pretty important, and we have a whole report on this from the LA city studies that I'll highlight at the end. And over here, if you're maximizing through conservation to minimize costs, you're probably going to see less water in the basin, probably returning to something maybe that looked like the pre-urban hydrology, where you didn't have streams flowing all year long. Now we can also look at this in terms of percent change. And this one's important, because here we see actually it's much less drastic in terms of percent change. So if you look at the percent of the historic simulated hydrology versus the optimized flows, up in those upper basins you see some increases actually, and then down here decreases. They look less drastic though in comparison to the total flow. And over here you look at minimizing costs. Here you again see more drastic differences, but you still see some increases in the upper basins. If you look at upstream and downstream differences, when I first made these graphs I was kind of confused, because essentially I divided up the upstream basins and the downstream basins, and you see here that for the flow maximization and the cost minimization results, you're actually in February getting a lot more water in the downstream basins than the upstream basins. This is average flows. And I was like, what? That doesn't make any sense. This is telling me what's different. And so what I realized, what I think is going on, is that it's medians versus averages. So it's extreme hydrology, extreme flows. You'll get a few years where you get a bunch of flows that'll boost your averages, but you really need to look at the middle ground, because most years you're going to see reduced flows. And then if you compare simulated and optimized results based on your over the course of the year here, with the average again, which is kind of using those the few extreme years to boost averages, you do see that the minimum cost method with more conservation is going to result in less flows in terms of the difference between historic and optimized hydrology. You do see more in the maximum flows model. But what this is actually telling me is that you're probably going to see, if you cut imported water and you're emphasizing conservation, you're probably going to see reduce stream flows, but you still, through infrastructure, have the chance to maybe improve the flows in the places where you want them to be improved. So once again, a highly engineered basin. I'll highlight these. There's been a recent New York op-ed by Mark Gold down at UCLA, and you might have seen it discussed a little bit in some of the news outlets. These are three of the couple of four watershed by watershed reports we have that detail the urban hydrologic modeling underlying parts of this work too. If you're interested, I encourage you to check these out. These are probably some of the most comprehensive reports for an urban system for the Los Angeles city that are available. It looks across the entirety of the integrated urban water management perspective, and they're really great. Katie Micah was the person in charge of putting these together. They're excellent reports. So here's a few links if you're interested in more. We have lots of detail online. We've got our Water Hub, which is a dynamic visualization site. We're in the process of updating that.